hope you found your way here during one of those quiet moments when the universe calls to you, when you're ready to drift into something extraordinary. Tonight, we're embarking on a journey to explore some of the most bizarre and magnificent objects in the entire cosmos. Objects so dense, so powerful, so utterly alien that they challenge everything we think we know about matter, space, and time itself. If you find comfort in these gentle explorations of the universe, I'd be grateful if you could hit that subscribe button and give this video a like. It helps the algorithm connect with more curious souls like us, people who find wonder in the deepest mysteries of space. It would also help me reach my goal of building this community of cosmic explorers who share a passion for understanding our place in this magnificent universe. The visuals are here to guide you, but there's absolutely no pressure to keep your eyes open. Feel free to close them, breathe deeply, and let your imagination soar through the cosmos at the speed of thought. Also, I'd love to know where you're watching from tonight. Drop your location and time in the comments below. Imagine for a moment that you could take our entire sun, with all its blazing fury and immense mass, and compress it down until it fits within the boundaries of a single city. Picture cramming all that stellar material, all those nuclear fires, all that gravitational might into a sphere no larger than Manhattan or Paris. This isn't science fiction. This isn't some impossible thought experiment. This is the reality of neutron stars, objects so incomprehensibly dense that they rewrite the rules of physics and challenge our most fundamental understanding of what matter can become. Welcome to this cosmic journey, where we'll explore the universe's most extreme creations, where we'll discover how the death of massive stars gives birth to objects more bizarre than anything our earthbound experience could prepare us for. We'll venture into realms where a teaspoon of matter weighs as much as 7 million elephants, where magnetic fields are trillions of times stronger than anything we can create in our most advanced laboratories, where time itself behaves in ways that would make Einstein smile with wonder. The story we're about to unfold isn't just about distant cosmic objects. It's about the very elements that make up your body, the gold in your jewelry, the uranium that powers our cities. It's about understanding how the universe creates its heaviest building blocks in moments of unimaginable violence and beauty. This is the story of neutron stars, and it begins in the heart of a dying giant. Picture a star so massive that our sun would seem like a mere candle flame beside a roaring bonfire. We're talking about stellar titans, stars with 8 times, 10 times, even 20 times the mass of our sun. These cosmic giants live fast and die young, burning through their nuclear fuel at rates that would make our sun seem positively conservative. For millions of years, these massive stars wage an epic battle between two fundamental forces: gravity pulling inward with relentless determination, and nuclear fusion pushing outward with the power of countless hydrogen bombs. Deep within the core of such a star, nuclear fusion works like the ultimate alchemist, transforming hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into silicon, and finally silicon into iron. This cosmic forge operates at temperatures exceeding 100 million degrees, pressures that dwarf anything we can imagine, creating the heavy elements that will one day become planets, asteroids, and yes, even the calcium in your bones and the iron in your blood. But iron changes everything. Iron is the cosmic party killer. the element that brings this stellar celebration to a sudden and catastrophic end. You see, fusing iron doesn't release energy, it requires energy. When a massive star's core becomes rich in iron, the nuclear fires that have sustained it for millions of years suddenly sputter and die. The outward pressure that has held the star together vanishes in an instant, and gravity finally wins its ancient battle. What happens next occurs faster than a human heartbeat. The core of the star, roughly the size of Earth but containing more mass than our entire Sun, collapses under its own weight. In less than a second, this stellar core shrinks from thousands of miles across to just a few miles in diameter. The matter becomes so compressed that the very atoms themselves are crushed beyond recognition. Imagine trying to squeeze a basketball until it becomes smaller than a marble, but instead of a basketball, you're compressing matter so dense that atomic nuclei touch each other directly. The electrons and protons that make up ordinary matter are forced together with such violence that they merge, creating an entirely new form of matter composed almost entirely of neutrons. This is the birth of a neutron star, and it's one of the most extreme events the universe has to offer. The collapse releases energy equivalent to the sun's entire output over billions of years, all unleashed in mere seconds. This energy blasts away the star's outer layers in a spectacular supernova explosion that can outshine an entire galaxy containing hundreds of billions of stars. For weeks or months, this single exploding star can be brighter than all the other stars in its galaxy combined, visible from distances of millions of light years. But at the heart of this cosmic violence, something even more extraordinary emerges. The collapsed core, now a neutron star, represents matter in its most extreme state. A sugar cube-sized piece of neutron star material would weigh as much as all the people on Earth. A teaspoon would have the mass of 7 million elephants. This isn't just dense matter, this is matter so compressed that it approaches the fundamental limits of what the universe allows. The surface gravity on a neutron star is approximately 100 billion times stronger than Earth's gravity. If you could somehow stand on its surface, you would weigh about as much as a mountain does here on Earth. A simple step would require more energy than climbing Mount Everest, but of course, you couldn't actually survive such conditions. The gravity would instantly flatten you into a layer just atoms thick. These stellar remnants spin with incredible speed, rotating hundreds of times per second. Imagine something with more mass than our sun, compressed into a city-sized sphere, spinning faster than a blender blade. The equator of such a neutron star moves at a significant fraction of the speed of light, creating relativistic effects that warp space and time around it. But perhaps most remarkably, neutron stars possess magnetic fields of almost incomprehensible strength. These magnetic fields are thousands to billions of times more powerful than anything we can generate in our most advanced laboratories on Earth. They're so strong that they can strip electrons from atoms at distances of hundreds of miles, creating plasma that glows with X-ray radiation. Some neutron stars, called pulsars, beam radiation from their magnetic poles like cosmic lighthouses. As they spin, these beams sweep across space, and if Earth happens to lie in their path, we detect regular pulses of radio waves, X-rays, or even visible light. These pulses are so precise they rival atomic clocks in their regularity, earning pulsars the nickname of nature's most accurate timekeepers. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, a graduate student who noticed strange, regular radio signals coming from space. The signals were so precise and regular that astronomers initially wondered if they might be artificial, perhaps messages from an alien civilization. They even nicknamed the first pulsar LGM-1, standing for Little Green Men. But as more pulsars were discovered, it became clear that these were natural phenomena, the lighthouse beams of spinning neutron stars. One of the most famous neutron stars is the Crab pulsar, located at the heart of the Crab Nebula. This cosmic lighthouse spins 30 times per second, sweeping its beams across space with clockwork precision. What makes the Crab pulsar particularly special is that we can connect it directly to a historical event. The supernova that created this neutron star was observed and recorded by Chinese astronomers in the year 1054. They called it a guest star because it appeared suddenly in the sky, becoming so bright it was visible during daylight for weeks. Today, nearly 1,000 years later, we can still see the expanding shockwave from that ancient explosion, now forming the beautiful Crab Nebula. At its center, the neutron star continues its rapid spin, accelerating particles to nearly the speed of light and flinging them into space, creating the ghostly wisps and filaments we observe with our telescopes. But not all neutron stars are created equal. Some possess magnetic fields so extreme they dwarf even typical neutron star magnetism. These objects, called magnetars, have magnetic fields about 1,000 times stronger than ordinary neutron stars. Their magnetic field strength reaches about 100 million Tesla, compared to Earth's magnetic field of roughly 50 microtesla. To put this in perspective, the magnetic field of a magnetar is so intense that it would be lethal to human life from a distance of about 600 miles. The magnetic forces would disrupt the electrical activity in your nervous system and even distort the very atoms in your body. These magnetic fields are so powerful, they can cause the neutron star's crust to crack and shift, releasing more energy in 1/10 of a second than our sun emits in 100,000 years. One magnetar, designated SGR 1806-20, produced such an intense burst of gamma rays in 2004 that it temporarily blinded satellites throughout the solar system and caused measurable changes in Earth's upper atmosphere, despite being located 50,000 light-years away. If this magnetar had been just 10 light-years from Earth, its burst would have caused a mass extinction event on our planet. The internal structure of neutron stars reveals even more cosmic strangeness. Beneath their solid crusts, which are harder than diamond and composed of atomic nuclei arranged in crystalline structures, lies a realm of exotic matter that pushes the boundaries of physics. As we journey deeper into a neutron star, the matter becomes increasingly strange and wonderful. In the inner regions, the extreme pressure creates phases of matter that physicists whimsically call nuclear pasta. Just as different types of pasta have different shapes, nuclear matter under these extreme conditions organizes itself into rod-like structures resembling spaghetti, sheet-like formations like lasagna, and other geometric arrangements that would be impossible under normal conditions. These pasta phases represent matter at densities where the usual rules break down, where protons and neutrons are squeezed so tightly together that they begin to overlap and merge in ways that challenge our understanding of nuclear physics. Some theorists speculate that at the very centers of the most massive neutron stars, matter might transform into something even more exotic, perhaps composed of fundamental particles called quarks, existing freely rather than bound within protons and neutrons. The temperatures inside newly formed neutron stars reach 10 million Kelvin or more, making them incredibly hot despite generating no new heat through nuclear fusion. They cool slowly over millions of years, but even ancient neutron stars maintain surface temperatures of around 1 million degrees, roughly 100 times hotter than our Sun's surface. These cosmic furnaces represent laboratories for physics under the most extreme conditions imaginable, conditions we could never hope to replicate on Earth. They allow us to test our theories about matter, gravity, and the fundamental forces of nature in regimes far beyond anything our terrestrial experiments can explore. But neutron stars aren't just cosmic curiosities existing in isolation. They play crucial roles in the grand story of the universe, serving as cosmic forges where some of nature's heaviest elements are created. When neutron stars collide with each other or with black holes, they create some of the most violent events in the cosmos. Explosions called kilonovae that can be detected from billions of light years away. Billions of light years away. These cosmic collisions represent some of the most spectacular and scientifically important events in the universe. When two neutron stars spiral toward each other, locked in an inexorable gravitational dance that lasts millions of years, they create ripples in the fabric of space and time itself. These gravitational waves, first predicted by Einstein over a century ago, carry the signature of their cosmic waltz across the universe at the speed of light. The final moments of this celestial ballet are both beautiful and catastrophic. As the neutron stars draw closer, their mutual gravitational pull becomes irresistible. They orbit each other faster and faster, spinning around their common center hundreds of times per second. Their surfaces literally touching as they merge into a single, incredibly dense object. The energy released in this cosmic collision is almost beyond comprehension, briefly outshining entire galaxies and sending shockwaves through the very geometry of space-time. On August 17th, 2017, humanity witnessed something extraordinary. The LIGO and Virgo gravitational wave detectors recorded the unmistakable signature of two neutron stars colliding in a galaxy 130 million light-years away. For the first time in history, we could both hear and see a cosmic event, detecting the gravitational waves from the collision and then observing the brilliant flash of light that followed. This detection marked a revolutionary moment in astronomy, opening an entirely new window into the universe. The gravitational waves told us about the masses of the colliding objects, their spins, and the dynamics of their final merger. But the light that followed revealed something equally remarkable: the birth of heavy elements in a process more violent and productive than anything we had previously imagined. During these neutron star collisions, conditions become so extreme that they create a cosmic alchemy unlike anything else in the universe. The collision ejects streams of neutron-rich matter at speeds approaching 20% the speed of light. In this incredibly hot, dense environment, neutrons are rapidly captured by atomic nuclei faster than they can decay, building up the heaviest elements in the periodic table through a process called rapid neutron capture. This is where the gold in your jewelry was born, where the platinum in catalytic converters originated, where the uranium that powers nuclear reactors first came into existence. A single neutron star collision can produce quantities of gold equivalent to several times the mass of Earth. scattered into space to eventually become incorporated into new stars, planets, and perhaps even living beings. The significance of this discovery cannot be overstated. For decades, astronomers puzzled over where the heaviest elements came from. While we understood that stars could create elements up to iron through nuclear fusion, and that supernova explosions could forge some heavier elements, the abundances we observed in the universe didn't match our theoretical predictions. The detection of the 2017 neutron star merger finally provided the missing piece of this cosmic puzzle. The explosion that followed this collision, called a kilonova, glowed with a distinctive spectrum of light that confirmed the presence of newly synthesized heavy elements. The color of the explosion changed over time as different radioactive elements decayed, painting space with hues that told the story of cosmic nucleosynthesis in real time. This wasn't just an explosion, it was the universe writing the periodic table in letters of fire and light. But neutron-star collisions aren't the only way these dense objects shape our cosmos. Individual neutron stars, spinning alone in the darkness of space, serve as natural laboratories for understanding physics under the most extreme conditions imaginable. Their immense gravitational fields warp space-time so severely that they provide natural testing grounds for Einstein's theories of general relativity. Near a neutron star, time itself runs slower compared to regions of weaker gravity, an effect called gravitational time dilation. If you could observe a clock on the surface of a neutron star from a safe distance, you would see it ticking noticeably slower than an identical clock in your spacecraft. This isn't science fiction. It's a measurable consequence of the curvature of space-time around these incredibly dense objects. The study of neutron stars has also revealed fascinating phenomena that challenge our understanding of matter itself. Some neutron stars exhibit sudden changes in their rotation rate, events called glitches, where the star suddenly spins slightly faster. These glitches are thought to result from interactions between the neutron star's solid crust and a superfluid ocean of neutrons flowing beneath it. A superfluid is a state of matter that flows without any friction or resistance, a quantum mechanical phenomenon that allows the neutron ocean to maintain its rotation even as the solid crust gradually slows down due to magnetic braking. Occasionally, the superfluid and crust suddenly couple together, causing the entire star to speed up momentarily as angular momentum is transferred from the interior to the surface. These glitches provide insights into matter under conditions we could never hope to replicate on Earth. The neutron superfluid inside these stars exists at densities millions of times greater than water, temperatures of millions of degrees, and pressures that exceed anything in terrestrial experience. Understanding how matter behaves under such extreme conditions helps us probe the fundamental limits of physics itself. Neutron stars also serve as cosmic beacons that help us navigate the universe and test our theories about space and time. Pulsar timing arrays, networks of radio telescopes that monitor the precise arrival times of pulses from multiple neutron stars, are sensitive enough to detect gravitational waves from supermassive black hole mergers occurring billions of light years away. The regularity of pulsar signals is so extraordinary that they rival atomic clocks in their precision. Some pulsars maintain timing accuracy better than 1 part in 10 billion, making them among the most stable natural clocks in the universe. This incredible precision allows astronomers to use pulsars as cosmic GPS satellites, helping spacecraft navigate through the solar system and providing reference points for mapping our position in the galaxy. The discovery of the first planets outside our solar system actually came from studying a pulsar. In 1992, astronomers detected tiny variations in the arrival times of pulses from PSRB 1257 plus 12. Variations that could only be explained by the gravitational influence of planets orbiting the neutron star. These pulsar planets represent some of the most extreme worlds imaginable, bathed in deadly radiation and subjected to gravitational forces that would tear apart any normal planetary material. The formation of such planets around neutron stars remains a mystery. They might be the remnants of worlds that somehow survived the supernova explosion that created the neutron star. Or they could be second-generation planets that formed from the debris disk left behind after the stellar explosion. Either way, they represent exotic worlds where the usual rules of planetary formation and evolution simply don't apply. As we peer deeper into the cosmos with increasingly sophisticated instruments, neutron stars continue to surprise us with their diversity and complexity. Some neutron stars appear to be completely isolated, spinning alone in the void with no companion stars or planetary systems. Others exist in binary pairs, locked in gravitational embrace with white dwarf stars, normal stars, or even other neutron stars. When a neutron star has a normal stellar companion, it can create some of the most energetic phenomena in the universe. The neutron star's intense gravity strips material from its companion, accelerating this stolen matter to tremendous speeds as it spirals inward. The infalling material heats up to millions of degrees, glowing brilliantly in X-rays, and sometimes erupting in thermonuclear explosions on the neutron star's surface. These X-ray bursts can release more energy in a few seconds than our sun emits in several years, creating brief but brilliant flares that can be detected from thousands of light-years away. The study of these eruptions provides insights into nuclear physics under conditions of extreme temperature and density, helping us understand how matter behaves when compressed to its ultimate limits. Some neutron stars in binary systems eventually accumulate enough material from their companions to push them over a critical mass threshold. When this happens, the neutron star can no longer support itself against gravitational collapse, and it transforms into something even more extreme: a black hole. This transition represents the final stage in the life cycle of the most massive stars, the ultimate victory of gravity over all other forces. The boundary between neutron stars and black holes remains one of the most fascinating frontiers in astrophysics. The exact mass limit where neutron star matter can no longer resist gravitational collapse depends on the equation of state of nuclear matter under extreme conditions, something we're still trying to understand through both theoretical calculations and astronomical observations. Recent detections of gravitational waves from neutron star collisions are helping to constrain this critical mass limit, providing clues about the fundamental properties of matter at nuclear densities. Each new detection adds pieces to the cosmic puzzle, helping us understand not just neutron stars themselves, but the nature of matter, gravity, and space-time under the most extreme conditions the universe can produce. The story of neutron stars is ultimately a story about transformation and extremes. These objects represent matter pushed to its absolute limits, gravity compressed into city-sized spheres, magnetic fields that dwarf anything in our earthly experience, and temperatures that would vaporize any known material. They're cosmic laboratories where the laws of physics are tested in regimes we could never hope to explore on Earth. But neutron stars are more than just exotic curiosities. They're the universe's heavy element factories, the sources of gold and platinum and uranium that make complex chemistry and ultimately life itself possible. They're natural clocks that help us navigate space and time, gravitational wave sources that reveal the dynamic nature of space-time, and laboratories where we can study matter under conditions that push the very boundaries of what physics tells us is possible. Every time you hold a piece of gold jewelry, you're touching atoms that were forged in the violent collision of neutron stars billions of years ago. Every time you check the time on an atomic clock, you're using technology that's calibrated against signals from neutron star lighthouses spinning in the depths of space. These connections remind us that we're not separate from the cosmos, but intimately connected to its most extreme phenomena. As you continue your journey through this cosmic night, remember that neutron stars represent both endings and beginnings. They mark the death of massive stars, but they also represent the birth of new possibilities, new elements, new ways of understanding the universe we call home. They're reminders that in the cosmos, destruction and creation are often the same process, that from the most violent events can emerge the building blocks of beauty and complexity. The precision of neutron star observations has revolutionized our understanding of fundamental physics in ways that extend far beyond astronomy. When we measure the timing of pulsar signals, we're essentially conducting experiments with matter under conditions that exist nowhere else in the observable universe. These natural laboratories allow us to test theories about the strong nuclear force, the behavior of matter at densities exceeding atomic nuclei, and the limits of what the universe allows. Consider the remarkable fact that we can measure the rotation of a neutron star with precision that rivals our best atomic clocks. When a pulsar's beam sweeps past Earth, we can detect variations in its arrival time measured in nanoseconds. This extraordinary precision allows us to study phenomena that would be impossible to observe any other way. We can measure how the neutron star's rotation gradually slows down as it loses energy through magnetic radiation, track sudden speed increases during glitches, and even detect the tiny wobbles caused by gravitational waves passing through our local region of space. These measurements reveal that neutron stars are far from simple uniform spheres of neutrons. Their interiors contain multiple distinct layers, each with its own exotic properties and behaviors. The outermost layer, the atmosphere, is only centimeters thick, but reaches temperatures of millions of degrees. Below this lies a solid crust made of atomic nuclei, arranged in crystalline lattices, but these aren't ordinary crystals. The nuclei are so neutron-rich that they would instantly decay if they existed anywhere else in the universe. As we journey deeper into the neutron star, the matter becomes increasingly strange. The nuclei grow larger and more exotic, containing hundreds of neutrons bound together in configurations that challenge our understanding of nuclear physics. Eventually, we reach depths where individual nuclei can no longer exist as separate entities. Instead, they merge into continuous structures that physicists have playfully named after Italian cuisine: nuclear pasta. These pasta phases represent matter organized in ways that seem almost artistic in their complexity. Imagine sheets of nuclear matter stretched thin like lasagna, or long cylindrical structures resembling spaghetti. all existing under pressures billions of times greater than anything we experience on Earth. The transitions between these phases may influence how heat and magnetic fields propagate through the neutron star, affecting everything from its cooling rate to the behavior of its magnetic field. At the very center of the most massive neutron stars, conditions become so extreme that even nuclear pasta may give way to something even more exotic. Here, the normal rules of nuclear physics might break down entirely, allowing quarks to exist freely rather than being confined within protons and neutrons. This hypothetical quark matter would represent a fundamentally different state of matter, one that may have existed in the universe only during the first microseconds after the Big Bang. The study of these interior structures isn't merely academic curiosity. The equation of state of neutron star matter, how pressure relates to density in these extreme conditions, directly determines the maximum mass a neutron star can achieve before collapsing into a black hole. This critical mass limit, somewhere between 2 and 3 times the mass of our Sun, represents a fundamental boundary in nature, the point where even the strongest nuclear forces surrender to the inexorable pull of gravity. Recent gravitational wave detections have begun to constrain this maximum mass by observing what happens when neutron stars collide. The waves carry information about the star's internal structure encoded in their frequency and amplitude patterns. By analyzing these cosmic signals, we can peer inside neutron stars in ways that would be impossible through any other means, mapping their internal structure through the language of gravitational waves. The magnetic fields of neutron stars create their own realm of extreme physics. These fields are so intense that they fundamentally alter the behavior of matter and light in their vicinity. Near a magnetar, the strongest type of neutron star magnet, the magnetic field becomes so powerful that it affects the very vacuum of space itself. Empty space, which we normally think of as completely empty, actually seethes with virtual particles that constantly appear and disappear due to quantum fluctuations. In the presence of an extremely strong magnetic field, these virtual particles can become real, creating matter and antimatter from pure vacuum energy. This process, called magnetic pair production, transforms empty space into a glowing plasma that radiates X-rays and gamma rays. The magnetic field also affects how light propagates, causing photons to split into multiple beams or change their polarization as they traverse the magnetized environment around the neutron star. The surface of a magnetar represents one of the most hostile environments imaginable. The magnetic forces are so intense that they can crack the neutron star's crust like an eggshell, causing massive starquakes that release more energy than our Sun produces in thousands of years. These crustal fractures can cause sudden rearrangements of the magnetic field, producing giant flares of gamma radiation that can be detected from across the galaxy. When a magnetoflare erupts, it sends a burst of high-energy radiation racing across space at the speed of light. If such a flare occurred from a magnetar just a few light years from Earth, it would deliver enough radiation to our planet to cause significant damage to our ozone layer and potentially trigger a mass extinction event. Fortunately, the nearest known magnetar lies safely thousands of light years away. But these events remind us of the incredible energies involved in neutron star physics. The formation of neutron stars also provides insights into one of the most fundamental questions in physics: the nature of the strong nuclear force under extreme conditions. This force, which holds atomic nuclei together, operates over extremely short distances under normal conditions. But in neutron star matter, where nuclei are pressed against each other, the strong force takes on new characteristics that we're still trying to understand. Laboratory experiments can only probe nuclear matter at densities up to a few times that of ordinary atomic nuclei. Beyond this limit, we must rely on astronomical observations of neutron stars to test our theories. Each new measurement of a neutron star's mass, radius, or cooling rate provides constraints on theoretical models of nuclear physics, helping us understand how matter behaves at the fundamental level. The cooling of neutron stars reveals another layer of complexity in these cosmic objects. When a neutron star first forms in a supernova explosion, its interior temperature can exceed 100 billion degrees. Over millions of years, this heat gradually radiates away into space, but the cooling process isn't uniform throughout the star. Different regions cool at different rates, creating temperature gradients that drive convection currents and affect the star's magnetic field evolution. The cooling rate depends critically on the types of particles present in the neutron star's interior. If exotic particles like hyperons or quarks exist in the core, they can accelerate the cooling process by providing additional pathways for energy loss through neutrino emission. By measuring the surface temperatures of neutron stars of different ages, astronomers can constrain the composition of neutron star matter and test theories about exotic particle physics. Some of the youngest neutron stars show signs of extremely rapid cooling, suggesting the presence of exotic matter in their cores. Others cool more slowly, indicating a more conventional composition dominated by neutrons, protons, and electrons. These observations provide a unique window into particle physics at energy scales that cannot be reached by terrestrial experiments. The magnetic field evolution of neutron stars presents another fascinating aspect of their physics. Young neutron stars often possess magnetic fields trillions of times stronger than Earth's, but these fields don't remain constant over time. The interaction between the magnetic field and the star's rotation creates electric currents that gradually dissipate the magnetic energy, causing the field strength to decay over millions of years. This magnetic field decay affects the neutron star's observable properties in complex ways. As the field weakens, the star's rotation slows down more gradually, affecting the timing of its pulses. The changing magnetic field also influences how efficiently the neutron star can accelerate particles and produce radiation, causing its brightness to vary over long timescales. Some neutron stars appear to undergo magnetic field reversals or reorganizations, sudden changes in field geometry that can dramatically alter their observable characteristics. These events may be triggered by instabilities in the star's magnetic field structure or by interactions between different regions of the neutron star's complex internal magnetic field. The study of neutron star magnetic fields has implications that extend far beyond astrophysics. These natural laboratories allow us to study plasma physics and magnetohydrodynamics under conditions that cannot be replicated on Earth. The insights gained from neutron star observations inform our understanding of magnetic fields in everything from laboratory fusion reactors to the magnetic environments around other stars and planets. Binary neutron star systems provide some of the most extreme examples of gravitational physics in action. When two neutron stars orbit each other, their immense gravitational fields create complex tidal effects that gradually rob energy from their orbital motion. This energy loss causes the stars to spiral closer together over millions of years, following a precise trajectory predicted by Einstein's general theory of relativity. The final moments of this cosmic dance occur with breathtaking speed. In the last few seconds before merger, the neutron stars orbit each other hundreds of times per second, their surfaces nearly touching as they spiral inward. The gravitational waves produced during this phase carry away enormous amounts of energy, equivalent to the mass energy of several suns converted entirely into gravitational radiation. As the neutron stars merge, their combined gravitational field becomes so intense that it tears both objects apart, creating a swirling maelstrom of neutron-rich matter heated to billions of degrees. Some of this matter falls into the black hole that likely forms from the merger, but significant quantities are ejected into space at velocities approaching 1/3 the speed of light. This ejected matter becomes the site of rapid nucleosynthesis, where atomic nuclei capture neutrons faster than they can undergo radioactive decay. The resulting isotopes are highly unstable and decay over timescales ranging from seconds to years, releasing energy that powers the kilonova explosion observed by telescopes across the electromagnetic spectrum. The optical brightness of a kilonova peaks within days of the merger, glowing with a distinctive red color caused by the radioactive decay of newly synthesized heavy elements. As weeks pass, the explosion fades and shifts toward infrared wavelengths, its spectrum revealing the fingerprints of exotic nuclear isotopes that exist nowhere else in nature. These cosmic forges operate with remarkable efficiency. A single neutron star merger can produce more gold than our Sun will create in its entire lifetime, despite the fact that our Sun will burn for billions of years, while the merger event lasts only minutes. This dramatic difference illustrates the incredible power of gravitational collapse and nuclear physics operating under the most extreme conditions imaginable. The debris from neutron star mergers doesn't simply disappear into space. Over millions of years, this material becomes incorporated into new generations of stars and planets, enriching the galaxy with heavy elements essential for complex chemistry and life. The gold in your smartphone, the platinum in catalytic converters, the rare earth elements in electronic devices, all trace their origins back to these violent cosmic collisions that occurred billions of years ago. This connection between neutron star mergers and terrestrial elements represents one of the most profound examples of cosmic recycling. The universe continuously transforms matter from one form to another. From the primordial hydrogen and helium created in the Big Bang, to the complex elements forged in stellar cores and neutron star collisions, and eventually to the rich chemical diversity we observe in planets, meteorites, and living organisms. As our technology advances, we're discovering new ways that neutron stars connect to our daily lives. The global positioning system relies on atomic clocks that are calibrated using astronomical time standards derived from pulsar observations. Deep space missions use pulsar timing to navigate through the solar system, treating these cosmic lighthouses as natural GPS satellites that can guide spacecraft across interplanetary distances. Future space missions may rely even more heavily on pulsar navigation. Unlike radio signals from Earth, which weaken with distance and can be blocked by planets or solar interference, pulsar signals provide reliable navigation references throughout the galaxy. This technology could enable autonomous spacecraft to navigate to other star systems without requiring constant communication with Earth-based mission control. The extreme physics of neutron stars also inspires technological innovations here on Earth. Research into neutron star matter helps scientists understand how to create and control extremely dense plasmas in fusion reactors. The study of neutron star magnetic fields provides insights into magnetic confinement techniques that could make fusion power more efficient and practical. Even the study of neutron star crusts, with their exotic crystal structures and unique material properties, inspires materials scientists to develop new types of ultra-strong materials and novel electronic devices. While we can't replicate neutron star densities on Earth, understanding how matter behaves under such extreme conditions helps us push the boundaries of material science in unexpected directions. The gravitational wave astronomy revolution has opened entirely new possibilities for studying neutron stars and testing fundamental physics. Each detection provides information about neutron star properties that was previously inaccessible, from their internal structure to their magnetic field configurations. As gravitational wave detectors become more sensitive, we'll be able to observe neutron star mergers from greater distances and with higher precision. Future gravitational wave observatories, including space-based detectors that can observe lower frequency gravitational waves, will provide even more detailed information about neutron star physics. These observations will help resolve fundamental questions about the equation of state of nuclear matter, the maximum mass of neutron stars, and the nature of matter under the most extreme conditions in the universe. The story of neutron stars continues to evolve as our observational capabilities expand and our theoretical understanding deepens. These objects serve as natural laboratories where the most fundamental forces of nature play out on cosmic scales, providing insights that connect nuclear physics to cosmology, quantum mechanics to general relativity, and the birth of elements to the evolution of life itself. As we delve deeper into the mysteries surrounding these cosmic titans, we encounter phenomena that stretch our understanding of reality itself. The precision with which we can study neutron stars has revealed that these objects exist in a delicate balance between competing forces, each one pushing the limits of what physics tells us should be possible. Consider the extraordinary dance of matter and energy that occurs when a neutron star spins at hundreds of revolutions per second. The centrifugal forces generated by this rotation are so immense that they nearly tear the star apart, held in check only by gravitational forces strong enough to crush atoms. This cosmic balancing act creates conditions where relativistic effects become not just measurable, but dominant in determining the star's behavior and observable properties. The surface of a rapidly spinning neutron star moves at velocities approaching 20% the speed of light. At such speeds, time itself begins to behave strangely. Clocks on the star's surface would run noticeably slower compared to those in the surrounding space, and the star's shape becomes distorted into an oblate spheroid, flattened at the poles and bulging at the equator by the tremendous rotational forces. These relativistic effects create observable signatures in the radiation we detect from neutron stars. The Doppler shifting of light from the approaching and receding sides of the star creates characteristic patterns in the observed spectrum. The gravitational redshift caused by the star's intense gravity shifts all radiation to longer wavelengths, while the rapid rotation creates complex modulation patterns that encode information about the star's size, mass, and internal structure. But perhaps most remarkably, some neutron stars demonstrate a phenomenon that challenges our most basic assumptions about stellar evolution. Occasionally, astronomers discover neutron stars that appear to be speeding up rather than slowing down, their rotation rates increasing over time through a process called accretion-induced spin-up. This occurs when a neutron star exists in a binary system with a normal star companion. The neutron star's intense gravity gradually strips material from its companion, forming an accretion disk of hot, glowing matter that spirals inward toward the neutron star's surface. As this material falls onto the neutron star, it transfers angular momentum, causing the dense object to spin faster and faster. The physics of this accretion process creates some of the most energetic phenomena observable in the universe. The infalling matter heats up to temperatures exceeding 100 million degrees as it approaches the neutron star, glowing brilliantly in X-rays. When this superheated material finally impacts the star's surface, it can trigger thermonuclear explosions that briefly outshine entire galaxies. These X-ray bursts represent nuclear fusion occurring under the most extreme conditions imaginable. The accumulated hydrogen and helium from the companion star undergoes explosive nuclear burning on the neutron star's surface, converting lighter elements into heavier ones in mere seconds. The energy released during these events can exceed the Sun's total output over several years, all concentrated into a sphere just a few miles in diameter. The study of these accretion processes has revealed that neutron stars can act as cosmic recycling centers, processing material from their surroundings and redistributing it throughout their local environment. The intense radiation and particle winds generated by accreting neutron stars can strip away the atmospheres of nearby planets, while simultaneously enriching the surrounding space with heavy elements created during surface nuclear explosions. Some binary neutron star systems exhibit even more exotic behaviors. When the companion star is itself a white dwarf or another neutron star, the system can undergo periodic outbursts as material is exchanged between the two objects. These systems, known as X-ray binaries, can switch between different states of activity, sometimes remaining quiet for years before suddenly erupting in brilliant displays of high-energy radiation. The gravitational interactions between close binary neutron stars create tidal forces that can literally reshape both objects. These tidal effects cause the neutron stars to become elongated, with their shapes responding to the gravitational pull of their companions. The resulting tidal heating can maintain high internal temperatures for millions of years, affecting the star's cooling rates and magnetic field evolution. As these binary systems evolve, they provide natural laboratories for studying general relativity in the strong field regime. The orbital decay caused by gravitational wave emission follows Einstein's predictions with extraordinary precision, confirming our understanding of space-time dynamics under the most extreme conditions. Each orbit brings the neutron stars closer together, gradually increasing the frequency and amplitude of the gravitational waves they produce. The final stages of binary neutron star evolution occur with dramatic suddenness. After millions of years of gradual orbital decay, the last few seconds before merger see the system undergo catastrophic acceleration. The neutron stars plunge toward each other at velocities exceeding 30% the speed of light. their surfaces distorting and stretching as tidal forces overwhelm even the incredible strength of neutron star matter. During these final moments, the neutron stars themselves become gravitational wave sources of unprecedented power. The energy radiated in gravitational waves during the last second of the merger exceeds the electromagnetic output of all the stars in the observable universe combined. This represents one of the most efficient energy conversion processes known to physics, transforming the orbital kinetic energy of the neutron stars directly into ripples in space-time itself. The merger event creates conditions that existed nowhere else in the universe since the first moments after the Big Bang. Temperatures reach trillions of degrees, densities exceed those found in atomic nuclei, and magnetic fields achieve strengths that would be lethal to human life from distances of thousands of miles. In this cosmic crucible, matter undergoes transformations that push the boundaries of nuclear physics into unexplored territory. The neutron-rich ejecta from these mergers carries the signatures of rapid neutron capture nucleosynthesis, creating isotopes with neutron-to-proton ratios far exceeding anything found in terrestrial laboratories. These exotic nuclei undergo radioactive decay chains that release energy over timescales ranging from seconds to millennia, powering the kilonova explosions that astronomers can observe across cosmic distances. The diversity of heavy elements produced in these events reflects the complex nuclear physics occurring during the merger process. Different regions of the ejecta experience different conditions of temperature, density, and neutron flux, leading to the synthesis of distinct groups of elements. The lanthanides and actinides, those rare earth elements essential for modern technology, are predominantly created in the most neutron-rich regions where traditional stellar nucleosynthesis cannot operate. This cosmic element production operates on scales that dwarf terrestrial manufacturing processes. A single neutron star merger can produce more platinum than has been mined in all of human history, more gold than exists in Earth's crust, and quantities of rare elements that exceed the total mass of our planet. Yet these cosmic factories operate for only minutes, demonstrating the incredible efficiency of nuclear physics under extreme conditions. The distribution of these newly created elements throughout the galaxy occurs through complex astrophysical processes that connect neutron star mergers to the formation of new stellar systems. The high-velocity ejecta from kilonovae creates expanding shells of enriched material that eventually interact with the interstellar medium, mixing heavy elements into the gas clouds from which future stars and planets will form. This cosmic recycling process operates over timescales of hundreds of millions of years, gradually increasing the heavy element content of the galaxy as successive generations of massive stars explode and neutron stars merge. The elements created in these violent events become incorporated into planetary systems, where they enable the complex chemistry necessary for life and technological civilization. The connection between neutron star physics and biological evolution represents one of the most profound examples of cosmic connectivity. The iron in our blood was forged in the cores of massive stars, while the iodine essential for thyroid function was created in neutron star mergers billions of years ago. The rare earth elements that enable modern electronics and medical imaging technology trace their origins to these same cosmic collisions. As our observational capabilities continue to advance, we're discovering new aspects of neutron star physics that challenge our theoretical understanding. Some neutron stars exhibit behaviors that don't fit neatly into existing categories, suggesting that these objects are even more diverse and complex than we previously imagined. Recent observations have revealed neutron stars with magnetic fields that appear to be decaying much faster than theoretical models predict, while others maintain strong magnetism for far longer than expected. Some pulsars exhibit timing irregularities that suggest complex internal dynamics, while others maintain clock-like precision that exceeds our best atomic timekeepers. The discovery of extremely massive neutron stars, with masses approaching the theoretical maximum for these objects, has forced physicists to reconsider their models of nuclear matter under extreme conditions. These observations suggest that neutron star matter may be stiffer than previously thought, capable of supporting more mass before succumbing to gravitational collapse. Conversely, the observation of very low-mass neutron stars challenges our understanding of the supernova explosion mechanism that creates these objects. The formation of neutron stars with masses significantly below the typical range suggests that stellar explosions can occur through pathways that don't conform to standard models of core collapse. The thermal evolution of neutron stars continues to reveal surprises about the composition and structure of these objects. Some neutron stars cool much faster than expected, suggesting the presence of exotic particles in their cores that provide additional cooling mechanisms. Others maintain high surface temperatures for unexpectedly long periods, indicating heating processes that aren't accounted for in current models. The magnetic field geometries of neutron stars display complexities that extend far beyond simple dipolar configurations. Multi-wavelength observations reveal magnetic field structures with multiple components, twisted field lines, and temporal variations that suggest ongoing magnetic field evolution throughout the neutron star's lifetime. These observational challenges drive theoretical advances in our understanding of dense matter physics, stellar evolution, and the fundamental forces of nature. Each new discovery forces scientists to refine their models, leading to deeper insights into the behavior of matter under conditions that cannot be replicated in terrestrial laboratories. The future of neutron star research promises even more revolutionary discoveries as new observational techniques and theoretical frameworks emerge. Advanced gravitational wave detectors will provide increasingly detailed information about neutron star interiors, while improved X-ray and radio telescopes will reveal subtle features in neutron star emissions that encode information about their magnetic fields and surface compositions. The development of multi-messenger astronomy, combining gravitational wave observations with electromagnetic and neutrino detections, offers unprecedented opportunities to study neutron star physics from multiple perspectives simultaneously. These coordinated observations will provide comprehensive views of neutron star mergers and their aftermath, revealing details about nuclear physics, gravitational dynamics, and element synthesis that no single type of observation could provide. Space-based telescopes optimized for studying neutron star emissions will eliminate atmospheric interference and enable long-term monitoring of these objects with unprecedented precision. These observations will reveal subtle changes in neutron star properties over time, providing insights into their thermal evolution, magnetic field decay, and structural modifications that occur over millions of years. The integration of artificial intelligence and machine learning techniques into neutron star research is accelerating the pace of discovery by enabling astronomers to identify patterns and correlations in vast datasets that would be impossible to detect through traditional analysis methods. These computational tools are revealing new classes of neutron star behavior and helping to connect observational data with theoretical predictions in ways that weren't previously possible. As we continue to push the boundaries of our observational capabilities and theoretical understanding, neutron stars remain at the forefront of fundamental physics research. These objects serve as natural laboratories where the most extreme conditions in the universe create phenomena that challenge our most basic assumptions about matter, energy, space, and time. The story of neutron stars is ultimately a story about the universe's capacity for creating complexity and beauty from the most violent and extreme events. These cosmic lighthouses, spinning in the darkness of space, connect us to the fundamental processes that shape the cosmos and make our existence possible. In studying them, we glimpse the universe's most profound secrets and discover our own place in the vast cosmic story that continues to unfold around us. The study of neutron stars has also revealed one of nature's most elegant demonstrations of how extreme conditions can create unexpected order from apparent chaos. When we examine the surfaces of these cosmic giants, we discover crystalline structures more perfect than any diamond, lattices of atomic nuclei arranged with mathematical precision that would make a crystallographer weep with wonder. These surface crystals exist under conditions so extreme that they challenge our most basic assumptions about how matter can organize itself. The nuclei are packed together at densities where the normal rules of chemistry simply cease to apply, yet they somehow arrange themselves into ordered patterns that extend across entire continents of neutron star real estate. The transition zones between different layers of neutron star matter create interfaces where physics becomes almost surreal. Here, matter exists in states that have no earthly equivalent, phases where the distinction between liquid and solid loses all meaning, where crystalline order emerges from nuclear chaos, where the very concept of an individual atom becomes a quaint relic of low-density physics. But perhaps what makes neutron stars most remarkable isn't their extreme physics or their role as cosmic element factories. It's their ability to serve as messengers from the deepest mysteries of existence itself. Every pulse we detect from these cosmic lighthouses carries information that has traveled across vast distances of space and time, bearing witness to events that occurred when the universe was young and violent. When astronomers first detected pulsars in 1967, they initially wondered if these regular signals might be artificial, perhaps communications from an advanced alien civilization. The signals were so precise, so mathematically regular, that they seemed almost too perfect to be natural phenomena. It took months of careful observation to realize that these weren't messages from little green men, but rather the natural consequence of neutron star physics operating under the most extreme conditions imaginable. This early confusion reveals something profound about the nature of neutron stars. These objects naturally generate patterns and rhythms that seem almost intelligent in their precision and regularity. They serve as cosmic metronomes, keeping time with an accuracy that rivals our most sophisticated atomic clocks, providing a natural rhythm that has remained constant for millions of years. The Crab pulsar, that cosmic lighthouse we discussed earlier, has been flashing its beacon across space for nearly 1,000 years since the supernova that created it. Chinese astronomers recorded its birth as a guest star that appeared suddenly in the sky, bright enough to be visible during daylight for weeks. Today, we can still observe the expanding shockwave from that ancient explosion, now forming the beautiful Crab Nebula with its ghostly wisps and filaments. At the heart of this nebula, the neutron star continues its relentless spin, 30 times per second, every second, for centuries on end. It's a cosmic clock that has been ticking since before the Renaissance, before the Americas were discovered, before humans had any understanding of what stars actually were. The precision is so extraordinary that if this celestial timekeeper had gained or lost even a single second over the past 1,000 years, we would notice the discrepancy in our observations. This temporal precision connects neutron stars to one of the most practical aspects of modern life: navigation and timekeeping. The global positioning system that guides our smartphones and aircraft relies on a network of atomic clocks that must maintain synchronization to within billionths of a second. These terrestrial timepieces are regularly calibrated against astronomical observations, including signals from pulsars that serve as the universe's most reliable chronometers. Future deep space missions will likely rely even more heavily on pulsar navigation. Unlike radio signals from Earth, which weaken with distance and can be blocked by planets or solar interference, pulsar signals provide reliable navigation references throughout our galaxy. Spacecraft traveling to other star systems could use these cosmic lighthouses as natural GPS satellites, determining their position and velocity by measuring the arrival times of pulses from multiple neutron stars. The technology required for pulsar navigation pushes the boundaries of precision measurement in ways that benefit many other fields. The ultra-stable clocks and sensitive radio receivers developed for pulsar timing find applications in everything from telecommunications to fundamental physics research. The techniques used to detect tiny variations in pulse arrival times have inspired new methods for measuring gravitational waves, testing Einstein's theories, and searching for subtle effects that might reveal new physics beyond our current understanding. But neutron stars offer more than just practical applications. They serve as natural laboratories where we can study physics under conditions that will never be replicated on Earth. The cores of these objects reach densities where quarks, the fundamental building blocks of protons and neutrons, might exist freely, rather than being confined within larger particles. This represents a state of matter that may have existed throughout the universe only during the first microseconds after the Big Bang. The magnetic fields surrounding neutron stars create environments where quantum mechanics and general relativity merge in ways that reveal new aspects of both theories. Near a magnetar, the magnetic field becomes so intense that it affects the very structure of empty space, causing virtual particles to materialize from the quantum vacuum and creating exotic forms of matter that exist nowhere else in the observable universe. These extreme magnetic environments also demonstrate phenomena that seem to violate our everyday understanding of how light behaves. Photons traveling through magnetar magnetic fields can split into multiple beams, change their polarization, or even transform into electron-positron pairs before recombining into new photons with different properties. The light itself becomes a probe that reveals the hidden structure of space and time around these cosmic monsters. The temperatures found on neutron star surfaces create another realm of exotic physics. Even ancient neutron stars maintain surface temperatures exceeding 1 million degrees, hot enough to strip electrons from any atoms that might exist there. This creates a plasma environment where matter exists as a sea of free electrons and nuclei, all moving at velocities that approach significant fractions of the speed of light. In this superheated plasma, the normal rules of atomic physics give way to relativistic quantum mechanics. Electrons orbit atomic nuclei at speeds where their mass increases noticeably. Their paths curve in ways that classical physics cannot predict, and their interactions with electromagnetic fields create spectral lines that encode information about the fundamental constants of nature under extreme conditions. These observations provide crucial tests of our physical theories in regimes far beyond anything achievable in terrestrial laboratories. When we measure the spectrum of light from a neutron star atmosphere, we're essentially conducting experiments with matter at temperatures, densities, and magnetic field strengths that push our theoretical understanding to its absolute limits. The cooling of neutron stars reveals another fascinating aspect of their physics that connects to deep questions about the nature of matter itself. When these objects first form in supernova explosions, their interiors reach temperatures exceeding 100 billion degrees. Over millions of years, this heat gradually radiates away. But the cooling process depends critically on what types of particles exist in the neutron star's core. If exotic particles like hyperons or free quarks are present, they can accelerate the cooling by providing additional pathways for energy loss through neutrino emission. Neutrinos, those ghostly particles that barely interact with ordinary matter, become the primary cooling mechanism for neutron stars, carrying away thermal energy at rates that depend on the detailed composition of nuclear matter at extreme densities. By measuring the surface temperatures of neutron stars at different ages, astronomers can effectively peer into their interiors and constrain theoretical models of nuclear physics. Some young neutron stars cool much faster than standard models predict, suggesting the presence of exotic matter in their cores. Others cool more slowly, indicating compositions dominated by conventional neutrons, protons, and electrons. These observations represent one of the few ways we can study nuclear physics at densities exceeding those found in atomic nuclei. The information encoded in neutron star cooling curves provides constraints on theoretical models that cannot be tested through any other means, connecting astrophysical observations to fundamental questions about the nature of matter under extreme conditions. The diversity of neutron star properties continues to surprise astronomers as our observational capabilities improve. Some neutron stars appear to be completely isolated, spinning alone in the darkness with no companions or surrounding material. These solitary objects offer the cleanest laboratories for studying neutron star physics, uncontaminated by the complex interactions that occur in binary systems or environments rich with surrounding matter. Other neutron stars exist in complex multiple star systems, locked in gravitational dances with white dwarfs, normal stars, or even other neutron stars. These systems create opportunities to study how neutron stars interact with their environments, how they accrete material from companions, and how their intense gravitational fields affect the evolution of nearby objects. The most exotic neutron star systems involve pairs of these dense objects orbiting each other in tight binary configurations. These systems serve as natural laboratories for testing general relativity in the strong field regime, where gravitational effects become large enough to measurably affect the orbital dynamics. The gradual decay of these orbits due to gravitational wave emission follows Einstein's predictions with remarkable precision, providing some of our strongest confirmations of general relativity's validity under extreme conditions. As these binary neutron star systems evolve toward their inevitable mergers, they provide advance warning of some of the universe's most spectacular events. Gravitational wave detectors can potentially observe the final stages of these cosmic collisions from billions of light years away, giving astronomers time to point telescopes at the expected location and capture the electromagnetic fireworks that follow. The multi-messenger astronomy revolution has transformed our ability to study these events by combining gravitational wave observations with traditional electromagnetic astronomy. When LIGO and Virgo detected the merger of two neutron stars in August 2017, telescopes around the world swung into action, capturing the kilonova explosion across the entire electromagnetic spectrum, from radio waves to gamma rays. This coordinated observation campaign revealed details about neutron star mergers that would have been impossible to obtain through any single type of measurement. The gravitational waves told us about the masses and spins of the merging objects, while the electromagnetic observations revealed the composition and dynamics of the ejected material, providing unprecedented insights into both neutron star physics and the cosmic origin of heavy elements. The success of this multi-messenger approach has inspired new observational strategies and technological developments designed to maximize our ability to study these rare but incredibly informative events. Networks of gravitational wave detectors are being expanded and improved to increase their sensitivity and sky coverage, while rapid response telescope systems are being developed to quickly locate and study the electromagnetic counterparts of gravitational wave sources. Future gravitational wave observatories, including proposed space-based detectors, will be able to observe neutron star mergers from even greater distances and with higher precision. These advanced instruments will provide detailed information about neutron star internal structure, the equation of state of nuclear matter, and the dynamics of matter under the most extreme conditions in the universe. The technological challenges involved in detecting gravitational waves have driven innovations that benefit many other fields of science and engineering. The ultra-stable laser systems, precision vibration isolation, and advanced data analysis techniques developed for gravitational wave astronomy find applications in everything from materials testing to quantum computing research. As we look toward the future of neutron star research, we can anticipate discoveries that will continue to challenge our understanding of fundamental physics. Each new observation reveals additional complexities in these objects, suggesting that neutron stars are even more diverse and exotic than our current theories predict. The next generation of radio telescopes will provide unprecedented sensitivity for detecting and timing pulsars, potentially revealing new classes of neutron star behavior and enabling more precise tests of general relativity and nuclear physics. These observations may uncover neutron stars with properties that don't fit current theoretical frameworks, forcing us to expand our understanding of what these objects can become. X-ray and gamma-ray observatories are revealing the high-energy environments around neutron stars in ever greater detail, showing how these objects accelerate particles to extreme energies and create some of the most luminous phenomena in the universe. The plasma physics occurring in neutron star magnetospheres provides insights into fundamental processes that govern magnetic field dynamics throughout the cosmos. The study of neutron star atmospheres and surface compositions promises to reveal new information about how matter behaves under extreme conditions of temperature, density, and magnetic field strength. Spectroscopic observations of these environments test our understanding of atomic physics in regimes where relativistic and quantum mechanical effects become dominant. Perhaps most remarkably, neutron stars continue to surprise us with their connections to other areas of physics and astronomy. The same theoretical frameworks used to understand neutron star matter apply to the cores of white dwarf stars, the interiors of giant planets, and even the conditions that existed during the first moments after the Big Bang. The magnetic field physics of neutron stars provides insights into dynamo processes that generate magnetic fields in planets, stars, and galaxies. The plasma physics occurring around these objects helps us understand similar processes in solar flares, galactic jets, and the environments around black holes. The nuclear physics probed by neutron star observations informs our understanding of stellar nucleosynthesis, supernova explosions, and the chemical evolution of galaxies. The gravitational physics demonstrated by neutron star systems tests our theories of space-time, causality, and the fundamental nature of gravity itself. As you continue your journey through this cosmic night, remember that neutron stars represent both the end points of stellar evolution and the beginning points of new physical understanding. They mark the death of massive stars, but they also represent the birth of new ways of comprehending the universe we inhabit. These cosmic laboratories operate under conditions so extreme that they reveal aspects of nature that remain hidden under more mundane circumstances. In their intense gravitational fields, powerful magnetic environments, and exotic matter compositions, we glimpse the universe's capacity for creating phenomena that transcend our everyday experience while remaining governed by the same fundamental laws that operate in our terrestrial laboratories. The precision of neutron star observations has reached levels where we can detect effects that were purely theoretical just decades ago. We can measure the wobble of space-time itself as gravitational waves pass through our local region of the universe. We can observe matter at densities where the normal distinction between particles and fields begins to break down. We can study magnetic fields so intense that they alter the fundamental properties of empty space. Each new measurement adds another piece to the cosmic puzzle, helping us understand not just neutron stars themselves, but the broader principles that govern how matter, energy, space, and time interact under the most extreme conditions the universe can produce. These discoveries connect us to the deepest mysteries of existence, while simultaneously revealing the profound unity that underlies the apparent diversity of cosmic phenomena. In the gentle darkness of space, neutron stars continue their ancient dance, spinning and pulsing with mathematical precision, creating heavy elements in violent collisions, and serving as beacons that guide us toward ever deeper understanding of our place in the cosmic story. They remind us that even in the universe's most extreme environments, beauty and order emerge from chaos, complexity arises from simplicity, and the fundamental laws of physics create phenomena more wonderful than anything our imagination could devise. These stellar remnants connect us to both the violent past of cosmic evolution and the peaceful precision of natural law. In their regular pulses, we hear the heartbeat of the universe itself. In their exotic compositions, we discover the building blocks from which all complexity emerges. In their extreme physics, we glimpse the elegant mathematical relationships that govern everything from quantum particles to galactic structures. As we drift deeper into contemplation of these cosmic wonders, we find ourselves part of the same story they tell. The elements in our bodies were forged in stellar cores and scattered by supernova explosions. The gold in our technology was created in neutron star collisions billions of years ago. The very atoms from which our thoughts emerge participated in the cosmic recycling processes that connect neutron stars to planets, stars to life, and the most extreme physics to the gentle complexity of consciousness itself. The relationship between neutron stars and the fundamental nature of reality extends into realms that challenge our most basic assumptions about what it means for something to exist. When we peer into the heart of a neutron star, we're not just looking at compressed matter. We're witnessing the universe's attempt to reconcile quantum mechanics with general relativity in a cosmic arena, where both theories must coexist despite their apparent incompatibility. Consider the quantum mechanical effects that govern the behavior of matter inside these stellar remnants. At the incredible densities found in neutron star cores, the normal rules of quantum mechanics become amplified to macroscopic scales. The Pauli exclusion principle, which normally operates at the level of individual atoms, now governs the behavior of an entire stellar core. This quantum pressure, arising from the fundamental requirement that no two neutrons can occupy the same quantum state, provides the ultimate resistance against gravitational collapse. But this quantum mechanical support operates in an environment where general relativity dominates the geometry of space-time itself. The result is a delicate balance between two fundamental theories of physics, each operating in its realm of maximum influence. The neutron star exists at the boundary between these domains, serving as a natural laboratory where we can observe how the universe resolves the apparent contradictions between quantum mechanics and gravity. The implications of this quantum relativistic interplay extend far beyond neutron stars themselves. These objects provide crucial testing grounds for theories of quantum gravity, those elusive theoretical frameworks that attempt to unify our understanding of the very small with our understanding of the very large. Every measurement of a neutron star's mass, radius, or cooling rate provides constraints on these fundamental theories, helping us move closer to a complete understanding of how the universe operates at its deepest level. The exotic matter, phases that may exist in neutron star cores, represent states of existence that push against the very limits of what the universe allows. In these environments, the familiar particles of everyday matter may undergo transformations so profound that they lose their individual identities entirely. Protons and neutrons might dissolve into their constituent quarks, creating a sea of fundamental particles that exists nowhere else in the present-day universe. This quark matter, if it exists, would represent a direct connection to the conditions that prevailed throughout the cosmos during the first microseconds after the Big Bang. In studying neutron stars, we might be observing relics of that primordial epoch, windows into a time when the entire universe existed in states of matter so extreme that they challenge our ability to describe them mathematically. The magnetic field environments around neutron stars create another realm where fundamental physics operates in ways that seem almost magical. These fields are so intense that they can literally create matter from empty space, causing pairs of particles and antiparticles to materialize from the quantum vacuum. This process transforms the region around a neutron star into a laboratory where we can study the deepest predictions of quantum field theory under conditions that cannot be replicated by any terrestrial experiment. The interaction between these ultra-strong magnetic fields and the relativistic plasma surrounding neutron stars creates phenomena that blur the boundaries between different branches of physics. Electromagnetic effects become gravitational. Quantum mechanical processes operate on astronomical scales, and the motion of charged particles generates radiation across the entire electromagnetic spectrum. These environments serve as cosmic particle accelerators, creating beams of high-energy radiation that can be detected from thousands of light-years away. The thermal evolution of neutron stars provides another window into exotic physics that operates over timescales ranging from seconds to millions of years. The initial heat generated during the supernova collapse creates internal temperatures that exceed those found anywhere else in the present-day universe. As this heat gradually radiates away, it reveals information about the fundamental properties of matter under extreme conditions. The cooling process depends critically on the types of particles that can exist at nuclear densities. If exotic particles like strange quarks or hyperons are present in the neutron star's core, they provide additional pathways for energy loss through neutrino emission. These ghostly particles, which barely interact with ordinary matter, become the primary cooling mechanism for neutron stars, carrying away thermal energy at rates that depend on the detailed physics of the strong nuclear force. By observing how different neutron stars cool over time, astronomers can effectively probe the composition of nuclear matter at densities that exceed anything found in atomic nuclei. Some neutron stars cool much faster than standard models predict, suggesting the presence of exotic phases of matter in their interiors. Others maintain high temperatures for unexpectedly long periods, indicating heating mechanisms that aren't accounted for in current theoretical frameworks. These observations provide some of our most stringent tests of nuclear physics under extreme conditions. The information encoded in neutron star cooling curves constrains theoretical models of the strong nuclear force in ways that complement and extend the results from terrestrial particle accelerator experiments. In effect, every neutron star serves as a natural laboratory where nuclear physics experiments have been running continuously for millions of years. The rotational dynamics of neutron stars reveal additional layers of complexity that connect to fundamental questions about the nature of matter under extreme conditions. The phenomenon of pulsar glitches, sudden increases in a neutron star's rotation rate, provides evidence for the existence of superfluids in stellar interiors. These quantum mechanical fluids flow without any resistance or friction, maintaining their motion even as the solid crust of the neutron star gradually slows down due to magnetic braking. The interaction between the superfluid interior and the solid crust creates a complex dynamical system where quantum mechanics operates on astronomical scales. Occasionally, the superfluid and crust suddenly couple together, transferring angular momentum and causing the entire star to speed up momentarily. These events provide unique insights into the behavior of quantum fluids under conditions of extreme density and gravitational stress. The study of neutron star superfluids has implications that extend far beyond astrophysics. The same theoretical frameworks used to understand these cosmic quantum fluids apply to laboratory superfluids and superconductors, helping us develop new materials with exotic electronic and thermal properties. The insights gained from neutron star physics inform our understanding of quantum phase transitions, many-body quantum systems, and the fundamental limits of how matter can behave under extreme conditions. The binary evolution of neutron star systems provides natural laboratories for studying gravitational physics in regimes where Einstein's theory of general relativity predicts its most dramatic effects. As two neutron stars spiral toward each other, their orbital dynamics encode information about the fundamental nature of space-time itself. The rate of orbital decay due to gravitational wave emission follows Einstein's predictions with extraordinary precision, providing some of our strongest confirmations that gravity propagates at the speed of light and carries energy and momentum through the fabric of space-time. But these systems also reveal subtle effects that test general relativity in ways that were impossible before the advent of gravitational wave astronomy. The tidal interactions between merging neutron stars create deformations in their shapes that depend on the equation of state of nuclear matter. These deformations leave measurable imprints in the gravitational wave signals, allowing us to probe the internal structure of neutron stars through the distortions they create in space-time itself. The final moments of neutron star mergers create conditions where general relativity and nuclear physics merge in ways that push both theories to their absolute limits. The formation of black holes from neutron star matter occurs at the boundary where quantum mechanical pressure can no longer resist gravitational collapse, marking a fundamental transition in the nature of matter and space-time. Understanding this transition requires theoretical frameworks that don't yet exist, theories of quantum gravity that can describe what happens when the quantum mechanical properties of matter encounter the curved space-time geometries of general relativity. Neutron star mergers provide observational data that will be crucial for developing and testing these future theories. The electromagnetic signatures of neutron star mergers reveal another aspect of extreme physics that connects nuclear processes to cosmic-scale phenomena. The radioactive decay of newly synthesized heavy elements powers kilonova explosions that can be observed across cosmic distances, creating natural laboratories for studying nuclear physics under conditions of extreme temperature, density, and neutron flux. The nuclear reactions occurring during these events operate through pathways that cannot be studied in terrestrial laboratories. The rapid neutron capture process that creates the heaviest elements requires neutron fluxes and nuclear reaction rates that exceed anything achievable on Earth by many orders of magnitude. The isotopes produced in these cosmic forges undergo decay chains that release energy over timescales ranging from seconds to thousands of years, creating a complex symphony of nuclear transformations that can be decoded through careful analysis of kilonova light curves and spectra. These observations provide crucial data for understanding how the universe creates its chemical diversity through nuclear processes operating under the most extreme conditions imaginable. The abundance patterns of heavy elements observed in stars, planets, and meteorites encode the history of neutron star mergers throughout cosmic time, connecting these violent events to the gradual chemical enrichment of galaxies and the eventual emergence of planets capable of supporting complex chemistry and life. The future of neutron star research promises discoveries that will continue to revolutionize our understanding of fundamental physics. Advanced gravitational wave detectors will provide increasingly detailed information about neutron star internal structure, while improved electromagnetic observatories will reveal subtle features in neutron star emissions that encode information about their magnetic fields, surface compositions, and thermal properties. The development of multi-messenger astronomy techniques will enable coordinated observations that combine gravitational waves, electromagnetic radiation, and neutrino detections to provide comprehensive views of neutron star physics from multiple perspectives simultaneously. These observations will reveal correlations and connections between different aspects of neutron star behavior that would be impossible to detect through any single type of measurement. Space-based gravitational wave observatories will open new windows into neutron star physics by detecting lower frequency gravitational waves that carry information about earlier stages of binary evolution. These observations will provide detailed maps of how neutron star systems evolve over millions of years, revealing the long-term effects of tidal interactions, magnetic field evolution, and mass transfer processes. The integration of artificial intelligence and machine learning techniques into neutron star research is accelerating the pace of discovery by enabling astronomers to identify patterns and correlations in complex data sets that would be impossible to detect through traditional analysis methods. These computational tools are revealing new classes of neutron star behavior and helping to connect observational data with theoretical predictions in ways that weren't previously possible. Theoretical advances in nuclear physics, quantum field theory, and general relativity continue to expand our ability to interpret neutron star observations and extract fundamental physics from astronomical data. The development of more sophisticated models of neutron star matter, magnetic field evolution, and gravitational dynamics provides increasingly precise predictions that can be tested against observational data. The technological innovations driven by neutron star research continue to find applications in fields ranging from materials science to quantum computing. The precision timing techniques developed for pulsar observations inspire new approaches to navigation, communication, and fundamental physics experiments. The data analysis methods used to extract gravitational wave signals from detector noise have applications in medical imaging, seismology, and industrial quality control. As our understanding of neutron stars continues to evolve, these objects remain at the forefront of humanity's quest to understand the fundamental nature of reality. They serve as cosmic laboratories, where the most extreme conditions in the universe create phenomena that test our theories, challenge our assumptions, and reveal new aspects of the physical laws that govern everything from subatomic particles to galactic structures. The story of neutron stars is ultimately a story about the universe's capacity for creating order from chaos, complexity from simplicity, and beauty from violence. These cosmic remnants remind us that even the most extreme events can give birth to phenomena of extraordinary precision and elegance. In their regular pulses, we hear the rhythm of space-time itself. In their exotic compositions, we discover the fundamental building blocks from which all complexity emerges. The precision with which we can now study these objects has reached levels that would have seemed impossible just decades ago. We can measure variations in neutron star rotation rates that correspond to changes smaller than the width of a human hair, occurring on objects located thousands of light years away. We can detect gravitational waves from neutron star collisions that occurred hundreds of millions of years ago, when life on Earth consisted of nothing more than simple single-celled organisms. These measurements connect us to cosmic events and physical processes that operate on scales ranging from the subatomic to the astronomical. Every pulse from a neutron star carries information that has traveled across vast distances of space and time, bearing witness to physics operating under conditions that push against the very limits of what the universe allows. The magnetic field strengths around these objects create environments where the normal rules of electromagnetism give way to exotic phenomena that exist nowhere else in nature. The gravitational fields near their surfaces warp space-time so severely that they provide natural testing grounds for Einstein's most profound insights about the relationship between matter, energy, space, and time. The internal structures of neutron stars represent matter organized in ways that challenge our most basic concepts about the nature of particles, forces, and fields. The transitions between different phases of nuclear matter create interfaces where physics becomes almost surreal, where the familiar categories of solid, liquid, and gas lose all meaning, where new forms of order emerge from the interplay between quantum mechanics and gravity. As we continue to probe these cosmic laboratories with ever-improving instruments and increasingly sophisticated theoretical frameworks, we discover that neutron stars are even more complex and fascinating than we initially imagined. Each new observation reveals additional layers of physics, connecting these stellar remnants to fundamental questions about the nature of space, time, matter, and energy. The study of neutron stars has become a multidisciplinary endeavor that brings together researchers from nuclear physics, condensed matter physics, general relativity, quantum field theory, and observational astronomy. This collaborative approach reflects the fact that understanding these objects requires insights from across the entire spectrum of physical sciences, each discipline contributing essential pieces to the larger puzzle. The technological challenges involved in studying neutron stars have driven innovations that benefit society in countless ways. The precision timing systems developed for pulsar observations have applications in global navigation systems, telecommunications networks, and financial trading platforms. The data analysis techniques used to extract weak signals from noisy backgrounds find uses in medical diagnostics, environmental monitoring, and industrial process control. The theoretical frameworks developed to understand neutron star physics contribute to our broader understanding of how matter behaves under extreme conditions. These insights inform the development of new materials, the design of fusion reactors, and our understanding of phase transitions in complex systems ranging from superconductors to quantum computers. Perhaps most remarkably, the study of neutron stars continues to reveal connections between apparently disparate areas of physics and astronomy. The same processes that govern neutron star cooling provide insights into the thermal evolution of planets and the dynamics of stellar cores. The magnetic field physics of neutron stars helps us understand dynamo processes in planets, stars, and galaxies. The gravitational wave emission from binary neutron stars tests our theories of space-time and causality under the most extreme conditions accessible to observation. These connections remind us that the universe operates as a unified whole, where the same fundamental laws govern phenomena across an enormous range of scales and conditions. Neutron stars serve as cosmic Rosetta Stones, helping us decode the relationships between different aspects of physical reality and revealing the deep unity that underlies the apparent diversity of cosmic phenomena. As you rest in this moment of cosmic contemplation, surrounded by the gentle darkness of evening or the soft light of morning, remember that you are connected to these distant neutron stars through bonds that transcend space and time. The heavy elements in your body were created in the violent collisions of these stellar remnants billions of years ago. The precise timing systems that coordinate our modern technological civilization depend on signals from neutron star lighthouses spinning in the depths of space. The mathematical relationships that govern neutron star physics are the same equations that describe the behavior of atoms in your cells, the flow of electricity through your nervous system, and the gravitational forces that keep your feet planted firmly on the ground. In studying these cosmic extremes, we discover not just the limits of physical law, but the fundamental principles that make our existence possible. The story of neutron stars is far from complete. Each new discovery opens additional chapters in this cosmic narrative, revealing new aspects of these remarkable objects and their role in the grand story of the universe. As our observational capabilities continue to advance and our theoretical understanding deepens, we can anticipate discoveries that will continue to challenge our assumptions and expand our appreciation for the elegant complexity of the cosmos we inhabit. In the gentle rhythm of your breathing, in the steady beat of your heart, in the electrical impulses that carry these thoughts through your mind, you participate in the same fundamental physics that governs neutron stars spinning in distant galaxies. The universe reveals its deepest secrets not through abstract mathematics alone, but through the lived experience of consciousness emerging from matter, complexity arising from simplicity, and wonder emerging from understanding. The neutron stars continue their ancient dance in the cosmic darkness, pulsing with mathematical precision, creating heavy elements in spectacular collisions, and serving as beacons that guide us toward ever deeper understanding of our place in the magnificent tapestry of existence. They remind us that even in the universe's most extreme environments, beauty and order emerge from apparent chaos, revealing the profound elegance that lies at the heart of physical reality. The study of neutron stars has revealed something profound about the nature of knowledge itself, about the limits of what conscious beings like ourselves can hope to understand about the universe we inhabit. When we peer into the heart of these cosmic giants, we encounter phenomena so extreme that they push language itself to its breaking point. How do you describe matter so dense that a marble-sized piece would outweigh Mount Everest? How do you convey the reality of magnetic fields so powerful they would be lethal from distances greater than the Earth-Moon separation? These aren't merely technical challenges or failures of imagination. They represent encounters with aspects of reality that exist beyond the comfortable boundaries of human experience. Neutron stars force us to expand not just our scientific theories, but our very conception of what it means for something to exist in this universe. They are cosmic teachers, showing us that the cosmos operates according to principles more strange and wonderful than our everyday experience could possibly prepare us for. The temperatures we encounter in neutron star physics span ranges that challenge our ability to comprehend scale itself. The cores of newly formed neutron stars reach temperatures exceeding 100 billion degrees, conditions so extreme that they dwarf the interior of our Sun by factors of thousands. Yet these same objects, over millions of years, cool to surface temperatures that, while still incredibly hot by terrestrial standards, represent a cosmic settling that connects to the gradual evolution of the universe itself. This cooling process isn't uniform or predictable. Different neutron stars cool at dramatically different rates, revealing hidden complexities in their internal structure and composition. Some maintain scorching surface temperatures for far longer than our models predict, suggesting internal heating mechanisms that operate through physics we're only beginning to understand. Others cool so rapidly that they must contain exotic forms of matter that provide pathways for energy loss through processes that exist nowhere else in nature. The diversity of neutron star cooling behaviors reflects a deeper truth about these objects. No two neutron stars are exactly alike. Each one carries the unique signature of the massive star that gave birth to it, the particular circumstances of its supernova explosion, and the billions of years of evolution that followed. Some spin hundreds of times per second, their surfaces moving at significant fractions of light speed. Others rotate sedately, taking seconds to complete each turn, their magnetic fields having gradually break their rotation over eons of cosmic time. This individuality among neutron stars parallels a fundamental characteristic of the universe itself. While the laws of physics are universal, their expression through specific objects and events creates endless variation and complexity. Every neutron star tells a unique story about stellar evolution, nuclear physics, and the interplay between matter and space-time under the most extreme conditions imaginable. The magnetic field evolution of these objects reveals processes that operate over timescales, ranging from microseconds to millions of years. Young neutron stars often possess magnetic fields of almost incomprehensible strength, created during the violent collapse that formed them. These fields aren't static. They evolve, decay, and reorganize themselves through processes that involve the complex interaction between the neutron star's rotation, its internal structure, and the surrounding plasma environment. Occasionally, these magnetic fields undergo sudden reorganizations that release energy equivalent to thousands of years of solar output in mere fractions of a second. These magnetic flares create bursts of high-energy radiation so intense they can temporarily blind satellites throughout our solar system. Despite originating from distances measured in thousands of light-years, the plasma physics occurring in neutron star magnetospheres creates natural particle accelerators more powerful than anything we could construct on Earth. Charged particles caught in these magnetic field configurations are accelerated to energies that approach the theoretical limits imposed by fundamental physics. The resulting radiation carries information about these acceleration processes across interstellar distances, allowing us to study particle physics under conditions that dwarf our most ambitious terrestrial experiments. But perhaps most remarkably, neutron stars serve as cosmic laboratories where we can observe the universe conducting experiments that we could never design or implement ourselves. The extreme conditions around these objects create natural tests of our most fundamental theories about the behavior of matter, energy, space, and time. Every observation of a neutron star provides data about physics operating in regimes that push our theoretical understanding to its absolute limits. The precision with which we can now study these objects has reached levels that seem almost miraculous. We can detect variations in neutron star pulse timing that correspond to changes smaller than the width of an atom occurring on objects the size of cities, located thousands of light years away. This precision allows us to use neutron stars as cosmic instruments for studying everything from the properties of interstellar space to the fundamental nature of gravity itself. Pulsar timing arrays, networks of radio telescopes that monitor dozens of neutron stars simultaneously have become sensitive enough to detect gravitational waves from supermassive black hole mergers occurring in distant galaxies. These observations open new windows into cosmic phenomena that operate on scales so vast they dwarf even neutron stars themselves, connecting the physics of stellar remnants to the dynamics of entire galactic systems. The binary neutron star systems that spiral toward eventual merger represent some of the most precisely predictable phenomena in the universe. The orbital decay caused by gravitational wave emission follows Einstein's equations with accuracy that exceeds our most precise atomic clocks. These systems serve as natural laboratories for testing general relativity under conditions where gravitational effects become strong enough to measurably affect the flow of time itself. When these cosmic dancers finally merge, they create conditions that briefly recreate the extreme environments that existed throughout the universe during its first moments. The temperatures, densities, and energy fluxes achieved during neutron star collisions approach those that prevailed during the primordial nucleosynthesis era, when the cosmos was less than 20 minutes old. The heavy elements created in these mergers carry the signatures of nuclear processes that operated when the universe was young and hot. By studying the isotopic ratios of elements like gold, platinum, and uranium in meteorites and stellar spectra, we can decode the history of neutron star mergers throughout cosmic time, tracing how these violent events have gradually enriched the galaxy with the chemical elements necessary for complex chemistry and life. This connection between neutron star mergers and biological evolution represents one of the most profound examples of cosmic connectivity. The iodine essential for human thyroid function was created in neutron star collisions that occurred billions of years before our solar system formed. The rare earth elements that enable modern electronics technology trace their origins to these same cosmic crucibles, where matter underwent transformations more extreme than anything occurring in the present-day universe. The study of neutron stars has also revealed unexpected connections between apparently disparate areas of physics. The same theoretical frameworks used to understand neutron star matter apply to the behavior of ultra-cold atomic gases in laboratory experiments, helping us understand phase transitions and many-body quantum systems under controlled conditions. The magnetic field physics of neutron stars provides insights into dynamo processes that generate magnetic fields in planets, stars, and galaxies throughout the cosmos. These connections remind us that the universe operates as a coherent whole, where the same fundamental principles govern phenomena across an enormous range of scales and conditions. Neutron stars serve as cosmic bridges, connecting our understanding of subatomic physics to astronomical phenomena, linking terrestrial laboratory experiments to cosmic-scale processes, and revealing the deep unity that underlies the apparent diversity of natural phenomena. The technological innovations driven by neutron star research continue to find applications that benefit society in unexpected ways. The ultra-stable timing systems developed for pulsar observations have revolutionized global navigation, enabling GPS accuracy that makes modern transportation and communication systems possible. The data analysis techniques used to extract weak neutron star signals from radio noise have found applications in medical imaging, environmental monitoring, and industrial quality control. The theoretical advances stimulated by neutron star physics have contributed to our understanding of superconductivity, quantum computing, and material science under extreme conditions. The insights gained from studying matter at nuclear densities inform the development of new materials with exotic electronic and thermal properties, potentially leading to revolutionary advances in energy storage, information processing, and manufacturing technologies. Future neutron star research promises discoveries that will continue to transform our understanding of fundamental physics and our technological capabilities. Advanced gravitational wave detectors will provide unprecedented information about neutron star internal structure, while improved radio and X-ray telescopes will reveal subtle details about their magnetic fields, surface compositions, and thermal evolution. The development of next-generation particle accelerators and nuclear physics facilities will complement astronomical observations by probing the properties of nuclear matter under conditions that approach those found in neutron star cores. These laboratory experiments will provide crucial data for interpreting astronomical observations and testing theoretical models of exotic matter phases. Space-based observatories optimized for neutron star studies will eliminate atmospheric interference and enable long-term monitoring campaigns that reveal subtle changes occurring over years or decades. These observations will provide insights into neutron star aging processes, magnetic field evolution, and the long-term stability of matter under extreme conditions. The integration of artificial intelligence and machine learning into neutron star research is accelerating the pace of discovery by enabling researchers to identify patterns and correlations in vast datasets that would be impossible to detect through traditional analysis methods. These computational tools are revealing new classes of neutron star behavior and helping to connect observational data with theoretical predictions in ways that weren't previously possible. As our observational capabilities continue to advance and our theoretical understanding deepens, neutron stars remain at the forefront of humanity's quest to understand the fundamental nature of reality. They serve as cosmic laboratories where the universe's most extreme conditions create phenomena that test our theories, challenge our assumptions, and reveal new aspects of the physical laws that govern everything from quantum particles to galactic structures. The story of neutron stars is ultimately a story about the universe's remarkable capacity for creating complexity and beauty from the most violent and extreme events. These stellar remnants remind us that destruction and creation are often the same process, that from the most catastrophic events can emerge phenomena of extraordinary precision and elegance. In their regular pulses, we hear the heartbeat of space-time itself. In their exotic matter compositions, we discover the fundamental building blocks from which all complexity emerges. In their extreme magnetic fields and gravitational environments, we glimpse the elegant mathematical relationships that connect quantum mechanics to general relativity, nuclear physics to cosmology, and the behavior of individual particles to the evolution of entire galaxies. The precision of neutron star physics reveals something beautiful about the nature of physical law itself. Despite operating under conditions so extreme, they challenge our ability to describe them. These objects follow mathematical relationships of extraordinary elegance and simplicity. The equations that govern their behavior are the same ones that describe the motion of planets around stars, the behavior of atoms in our bodies, and the propagation of light across cosmic distances. As we reach the end of our cosmic journey together, we've discovered that neutron stars are far more than just stellar remnants spinning in the darkness of space. They are the universe's most extreme laboratories, cosmic forges that create the heaviest elements, and natural clocks that keep time with mathematical precision across billions of years. From their violent birth in supernova explosions to their role in gravitational wave astronomy, these remarkable objects connect us to the deepest mysteries of existence itself. The next time you hold something made of gold or platinum, remember that you're touching atoms forged in the collision of neutron stars billions of years ago. Sweet dreams, fellow cosmic wanderers, and thank you for exploring the universe's most extraordinary phenomena with me tonight.